Today we'll be presenting on the twin field quantum key distribution. Introduction to the quantum key distribution. We'll start off with the BB84 protocol. So Alice chooses a string of bits 0 and 1 random, and then chooses a random basis, and then sends a qubit to Bob depending on this information. Bob then measures the qubits in random basis of his choice. They then compare the measured results and keep the bits where the basis matches. Thus, the leftover bits will become your key. BB84 is only secure if Alice sends single photons, which is hard to achieve experimentally. It is prone to simple photon splitting attacks, where if you send multiple photon sources, Eve can take one of the photons without Bob knowing, and then she can obtain the key. Now we'll introduce the decoy state. So Alice needs to be able to send phase randomized and randomized intensity of the signal. So intensity means the amount of photons sent, which is characterized by mu for each signal. Aside from the signal states, Alice also sends decoy states, which is identical to signal states, but with a different mu value. Eve cannot tell the difference between decoy state and a signal state. The only information she has is the amount of the photons that's sent. With the sent decoy states and the signal states, Alice and Bob can calculate an upper bound for the quantum bit error rate. If Eve tries to perform photon splitting attack, Alice and Bob can compare their error rates with the detection rates, thus catching any eavesdropper. More specifically, they can gather information on how many single photon and multi-photon pulses were detected, and thus detect any photon splitting attacks.
What is twin field quantum key distribution? Twin field quantum key distribution, or QKD, is a type of quantum key distribution that doubles the distance between the people sharing the key without greatly reducing the transmission rate. In conventional QKD, Alice has to send a quantum signal directly to Bob over a potentially noisy optical fiber. In this protocol, Alice and Bob both send a quantum signal to a person in between, which we will call Charlie, instead of Alice sending a signal to Bob. This means Alice and Bob can be twice as far apart without changing the length of optical fiber. Alice and Bob each choose a key, a string of bits or zeros and ones, and an additional random phase for each bit. A phase is a value from 0 to 2 pi, or from 0 to 1 full revolution, and it encodes a shift or delay in the wave function of a photon. For each bit, Alice and Bob both send a signal to Charlie, with the phase determined by the chosen bit and the additional random phase. If the bit is 0, the phase of the wave sent is just the random phase. But if the bit is 1, the phase is pi, or a half wavelength, in addition to the random phase. Since the random phase is, well, random, an eavesdropper looking at the signal cannot distinguish between a 0 and a 1 without knowing the random phase. Like in BB84, any attempt to directly observe the phase of the signal will yield incomplete information to the observer and will affect the signal, revealing to Alice and Bob the presence of a malicious party. When Charlie receives the signals, he sends them to a device called a Mach-Zehnder interferometer that tells him whether the phases are the same or a half wavelength apart without revealing the actual phases. Since Charlie does not learn the actual phases, even he does not need to be completely trustworthy, as there is no way for him to determine the actual bits used in the key. Charlie then publicly reveals the results of his measurements, and Alice and Bob reveal the random phases they added to their signals. If the random phases are neither nearly the same nor nearly a half wavelength apart, Alice and Bob both throw out the bit corresponding to that signal. Otherwise, Alice and Bob use Charlie's result and the comparison between the random phases to determine how their chosen bits compare to each other as shown in the table. Afterwards, if Bob's bit is different from Alice's, he flips its value. By the end, Alice and Bob are nearly certain to have a matching string of bits, without ever revealing them in any way an eavesdropper can detect. To repeat, the improvement comes from the fact that Alice and Bob don't need a quantum connection directly to each other, and they don't even need to trust their intermediary.
From its inception by Luca Marini et al. In 2018, twin-field quantum key distribution has been realized experimentally with great success, and it remains an active area of study. There have been many advances in the past 7 years. In 2018, Minder et al. Were the first to use twin-field quantum key distribution to experimentally break the rate distance limit of quantum key distribution that doesn't use quantum repeaters. In 2022, Wang et al. Demonstrated twin-field quantum key distribution at impressive distances, including a rate of 368 bits per second at a distance of 511 kilometers, and a rate of 0.014 bits per second at a distance of 833 kilometers. In 2023, Zhou et al. Proposed a way to perform twin-field quantum key distribution without a closed-loop Mach-Zehnder interferometer that automatically synchronizes laser frequencies between Alice and Bob. These changes reduce the auxiliary fiber installation overhead and make twin-field quantum key distribution viable with the optically switched setups required for larger networks. Also in 2023, Wai Lu et al. Demonstrated secure twin-field quantum key distribution at a distance of 1,002 kilometers with a bit rate of 0.0011 bits per second. For reference, France is about 1,000 kilometers wide, and California is about 1,200 kilometers tall. In 2024, Yu et al. Proposed a twin-field quantum key distribution scheme called no-interfering twin-field quantum key distribution that uses polarity information rather than phase information. It performs slightly better than an equivalent phase-based twin-field quantum key distribution scheme. This year, Si Lu et al. Proposed using particle swarm optimization for twin-field quantum key distribution parameters like the intensities of the signal, decoy, and vacuum states. This optimization algorithm is 3 orders of magnitude faster to perform than an exhaustive parameter search, and it's better suited for the real-time response needed for internet-scale key distribution. Twin-field quantum key distribution remains an active area of research. It promises to be a working framework for quantum internet-scale key distribution without requiring massive investments into quantum repeater research. And it allows provably secure key generation over longer distances than ever before. Thank you for watching.